Hello everybody, Cal here with section 16.1, vector fields. So we're getting into chapter 16 here, which is vector calculus, and this is the section where we introduce the basic object that we're going to be working with, which is vector fields. Most of this section is taken up with examples of various types of vector fields. Let's kind of page through it. What we have here on page 1080 is just a number of pictures of various vector fields. Your book gives some examples of vector fields, and it's introducing something it's calling a velocity vector field, where you have like air moving around a region, or water flow throughout a region, or airflow throughout a region, and you're recording the velocity of each point of air or water in the region. And so your book calls this a velocity vector field. This is not a terribly important type for our purposes, but I don't know that I'm ever going to really use, hey, this is a velocity vector field. But at the same time, it's a good application of vector fields. So you can kind of see what's going on here. At each point in the region, we're drawing a little arrow of how fast that point is moving, which is fine. Then your book talks about force field, which is, you could pretend that, well, it doesn't really have pictures, but you could pretend that, at each point in my region I've got a force pointing, acting on that point. And we'll see an example of that later, I suppose. In general, a vector field is a function whose domain is a set of points in R2 or R3, and whose range is a set of vectors also in R2 or R3. You can really think of a vector field as being a function from R2 to R2, or a function from R3 to R3. It assigns to each point in R2 a two-dimensional vector, or it assigns to each point in R3 a three-dimensional vector. I really like this definition, where you can think of a vector field as being a function that takes in a vector and spits out a vector. You see a number of pictorial examples on the left here, and our first few examples are just going to be of drawing and visualizing vector fields. You should work through example 1. You should kind of look through the pictures over here in figures 6, 7, and 8. And you should try to work through example 2. I mean, you should be able to give a basic sketch of a vector field. This isn't too terribly hard. I wouldn't expect you to sketch anything too terribly complicated, like in figures 10, 11, or 12. And you can see, by the way, that even with relatively simple equations, you can get some pretty complicated looking vector fields. We're not going to be going deeply into the visualization of various vector fields here. I just want you to have some sense of what they look like. Examples 3, 4, and 5 on the next page are other various common sorts of vector fields, and I would read through them if I were you. A more important sort of vector field for our purposes is going to be a gradient field. If I have a scalar function, little f, of 2 or even 3 variables, then I can create its gradient vector field, which is just going to spit out the gradient of f at each point. This really is a vector-valued function, so the gradient is a vector-valued function. And you'll note, by the way, your book just mentions it offhand, notice that the gradient vectors are going to be perpendicular to the level curves of your function. And for us, it's going to be important whether a vector field is a gradient vector field. And such a vector field is called a conservative vector field. It's a conservative vector field if it is the gradient of some scalar function. In which case that scalar function is called a potential function for a vector field big F. Not all vector fields are conservative, but conservative ones do arise frequently and are going to be relatively important. We will learn later on how to tell whether a given vector field is conservative, how to tell whether it's the gradient of some function. But that's just a basic introduction to vector fields, and that's it for this section.